Dynamic facades are changing the definition of modern architecture and sustainability through numerous innovations and smart techniques adaptive to any kind of building skin.
Our project is a research center located in London City, which is famous for tourist destination and number of educational facilities. It has a temperate climate with lowest temperature recorded in January and highest in June.
The site accessibility is shown with red for main roads and access arrows along with the solar path. The site topography is surrounded by different educational and residential buildings, which serves its purpose being an educational research center.
The research center is a two-story facility which is designed at an angle to enhance interaction and convenience to the public from neighboring educational facilities.
We have designed our dynamic facade with the concept of biomimicry, which is one of the latest innovations since past few decades in the field of designing sustainable architecture. The facade concept derived from the plant touch-me-not or Mimosa pudica. As you can see, the plant folds its leaves when in contact with external stimuli. This movement is called nastic movement, which is mimicked in our dynamic facade along with the form leaf as our design. We started our design process with sketches, ending up with dynamic unit which is repeatable and applicable to any building types. In our dynamic facade, the touch-me-not leaves are converted into louver fins, which has two movements, angular rotations horizontally and vertical folding of the louver blades. The louvers goes from its fully closed position to different angles, reaching to 90 degrees and folds vertically to fully open the facade. Notice how the facade is mimicking the nastic movement on the touch-me-not plant.
A single unit of facade is up to 100 cm in length and 78 cm in width, with the louver blades being 2 cm in thickness made up of fiberglass reinforced plastic. The louvers are connected to rotary pivots recessed in vertical aluminum beams. They are connected to an energy-sufficient servo motor, which enables and controls the facade movements.
Here is a basic installation detail of our facade to the building envelope, with the aluminum beams carrying the load of the facade units along with the support panels and support beams.
Let us start with our IEA simulation, where we have chosen 3 seasons: winter January 17, spring March 28, and summer June 27. 3 times per day were chosen: 9 a.m., 12 p.m., and 4 p.m. This is the solar path for the full year. Here we can see the winter sun exposure, based on which we have derived our dynamic facade strategy. We chose 2 most suitable louver angles, 45 and 90 degree, and the open position of facade. According to the London weather, external temperature on January 17 is -3 degrees, which lead us to simulate both base case and facade case with the heating system turned on. The temperature in both cases were consistent, with comfort range with solar gain slightly reduced, as we require it for passive solar heating. With the help of our dynamic facade, we have managed to reduce 25% heating load in winter. Comparing the base case with facade case for daylighting and glare control, we can clearly see we achieved the comfortable visual range. The minimum being 300 lux and within the range of 300 to 500 lux according to BIM and CIBSE manual. The daylight factor in facade case falls within the range of 2 to 3%, which is the standard for higher educational center by BIM UK.
Going to the spring season, we have followed the same technique to derive our facade strategy. Scenario, we turned off the heating and cooling systems for the facade case analysis to eliminate the need for HVAC system. The temperature in facade case tends to be within the comfort range without any HVAC, along with the solar gain reduced to 50%, which will provide enough passive heating without the risk of overheating as mentioned in SAP appendix for overheating threshold. Hence, we achieved to eliminate the need for HVAC. The base case for spring scenario had excessive illuminance of more than 950 lux. We managed to bring down the illuminance level and daylight factor to the comfortable range in accordance to a research done in UK for different building types.
In summer season, we drive the facade strategy based on the sun exposure analysis. We tried to switch off the cooling system in summer with kinetic facade, but the temperature turned out to be above the maximum range.
So we turned on the cooling system for both cases due to greenhouse effect, keeping internal temperature consistent but reducing solar gain to a significant amount to regulate overheating. Through this strategy, we have reduced 60% cooling load in summer. Similar to winter and spring, the visual comfort was achieved with our kinetic facade.
We conducted internal wind analysis for summer to evaluate natural ventilation, where we found the internal air velocity of base case crossing the recommended range given by ASHRAE, which is 0.1 meter per second and achieved after our facade application.
To conclude the IES analysis, we achieved the comfort goal of our project building as you can see in the following psychometric charts.
As a part of renewable energy, we covered the roof with PV system.
The PV system provided us with 31,618 kWh annually, which will cover energy produced by the servo motor, which is 23,328 kWh annually. Going to the BREEAM assessment method for UK, the rating depends on total percentage scores, where health and well-being section contribute 8% for shell and core only projects. Overall, our dynamic facade fits in the criteria of visual comfort and few criterion of IAQ, thermal comfort, safe and healthy surrounding and transport assessment, gaining 10 credit in total.
In the end, we would like to highlight that our dynamic facade is going to maximize sustainability and conserve energy.